Okay, so I'm going to talk about module checking of SDL systems and the technology we use to do that. So first, an introduction, because I'm not sure everybody is familiar with SDL. So SDL stands for Specification and Description Language. It's a standard from the International Telecommunication Union, and it was aiming at describing telecommunication protocols, and it has been used by different organizations to, for example, to describe 3G or even before X25. I don't know if you're familiar with these protocols, so it has been quite widely used in telecommunication, but also in other domains where you need to be precise in the description of interaction between entities, like telecommunication protocols. So it's also used in space and defense industries because it's quite precise. There's quite a strong semantic. It's completely asynchronous. It's based on messages. You exchange messages, and you don't wait for. You can wait for an answer, but I mean you're not stuck waiting for an answer. It's not like a MATLAB, which is synchronous, where you have to wait for the operation to complete. You can send a message, and then you wait for an answer as a state machine. There are data types within SDL. So you can have counters, you can have arrays, you can have floats and everything. That's sometimes the discussion we had this morning. Maybe you can consider SDL as almost a programming language, because you have all this action language and data types within it. But still, it was not meant to be programming language, but it was meant to be precise enough so that if you read the model, there is no interpretation possible. Okay, everybody understand the same behavior. Okay, so that's very important. Huh? The behavior of the model is properly defined by the standard itself. So I'm the CEO and founder of PragmaDev, and PragmaDev, what we have is we have a tool based on SDL, and among other things, we have an SDL executor, so we can execute SDL models. We can do step by step in the model and see if we have variables inside. We can see what's going on inside. So when you have an executable modeling language, an executable model, it's very tempting to explore the model automatically, what we call model checking. Okay, so basic idea is have a machine try all possible paths of execution and maybe find some problems like deadlocks. Maybe you can verify properties, or you can also do some model-based testing based on some target. You know, maybe I want to cover that symbol. You know, build a scenario that goes to that symbol, or maybe you have some error situation, you know, divide by zero things, execution errors. So there are a lot of motivation to work on model checking. Now, because it's message based, it's asynchronous. It has implicitly a huge number of possible states. So what I call state is not one state of one finite state machine. It's the overall state. So it's the combination of all the states of all the state machines with the value of the variables, with the pending messages and everything. Okay, that's the global state. So each time you execute something, you move into that state space, and when you do the model checking, you do the state space exploration. So if you want to explore everything, you want to explore any order of messages, any value of parameters. And also there's another issue, is that these models, actually, they never end. They keep running all the time. You know, it's like a telecommunication protocol. It's always on. Okay, it keeps going. So you understand from the start, it's quite tricky by nature. So what we did, we've been doing that for quite some time, try to different technologies, is to do some what we call, well, basic exploration. It's like, okay, we'll try all the values. okay, basically. And we let the tool try to simplify things, and oh, I've been there before, so I can cut that path, and so on. And we also tried symbolic execution. So symbolic execution is different, is that you're looking into the model, and then you know what are the interesting values to explore. So you want to explore them all, you just explore a few of them, okay? And what we have tried recently, and what I will present here in more detail, is the language agnostic exploration we have done with Bretagne. And Cyprian is here, so he can answer all the detailed question about that. If I go back to the main issues we had when we did some experiments, first, if you use a tool that is specialized in model checking, they usually have their own language. Okay? Even though the language might be very close to what you have in your modeling language, like SDL or anything else, it's not the same. So you will always have some issues to translate your concepts to the concept of the new language. So that's one issue. You're not sure that what you're exploring in the model checking tool is conform to what you have put into your model. And sometimes some constructs are basically not translated, so it's not easy. So that's really a big issue when you have to translate to another tool. Same thing if you do symbolic execution, you have to sort of translate the model anyway into some representation, it's sometimes very difficult to translate some concepts. And anyway, the complexity of analyzing the model as a big equation is very high. We thought it would be simpler, but actually it's as complex as exploring all the states in the state space. So because we have issues when you explore, you try to reduce the state space. But if you translate to another language, a model checking language notation, you do the state space reduction in that language, not in the source language you wrote your model with. So it's a bit of a problem. Or you have to modify your source model, and that's not something you want to do either, because you're modifying your model. So you don't want to do that. In a previous project, we worked with OBP2, so that's the tool from Bretagne, and their approach was very different. Because what they do is they don't have their own execution engine. They rely on the execution engine of the source model. So they have to interact with the execution engine. They ask, I'll show you the interface. They interact with the execution engine. And we thought, oh, well, that's quite interesting, because then there's no misinterpretation of the model. It's my model. There's no misinterpretation of the execution semantics. And even if I have maybe some execution semantics interpretation from our tool, well, it will stay valid there. And we tried that on BPMN models, business process model notation models, which are quite simple because they don't have data in them, so the number of states is quite reduced, but it was quite satisfactory. So we thought, okay, well, we'll try that on SDL models, which are quite more complex, and we'll see how it goes. So maybe that's the interface between the executor. So it can be any model executor. Right? So in that case, it's our SDL model executor and the observer-based prover, because that's what it stands for, OBP. And so OBP actually asked for the model executor what is the state of the model, so the overall state. And the idea is that OBP can ask the executor, can you go back to that state, please? Because when you do exploration, you go one branch and then you go back and then another branch and you explore like this. So OBP is driving the executor. It's setting the states. What are the viable execution, the possible transition to execute? Okay, execute this one or this one, and then maybe go back to another state, and so on. And OBP can evaluate properties. So we use a property sequence chart to express the properties. But again, OBP will not evaluate the atomic properties. It will ask the executor to evaluate the atomic properties. It will evaluate complex properties that combines these atomic properties. Okay, so that when you travel in the state space, it will evaluate the overall property. So what still we had some state space explosion issues. Okay, it's not because we use our own execution tool that we have resolved that. So we still have this issue. So first we had to deal with the instances, because when you have dynamic process creation like you have in SDL, you create a process, it dies, and you recreate one. But the PID of the process is not the same. So the state, the overall state is not considered to be the same, but actually it's the same. PID doesn't matter actually. Okay, what matters is the state within the process I have just created, the pending messages, or maybe the value of the variables. So we had to sort this out. First, sort by name, sort by state, sort by value of variables, and so on. You know, and then assign automatically PIDs, so that if you create, delete, and recreate a process, you will find the same state because they are equivalent. So that was one of the thing we did. The other thing is that when you send messages with parameters, not all the values of the parameters are interesting. Okay, it's could be evaluated automatically. I mean, you could go into the model and see, you know, is that value used somewhere? You know, if not, maybe get rid of it. But sometimes it's very tricky because you need a full analysis, a full understanding of the model. So what we did first is we said, okay, we'll let the modeler decide which values are interesting. Okay, he wrote the model, so he knows. Okay, but we don't want the model to be modified. So we have like a configuration panel for the exploration, and we say, okay, this parameter, you don't have to try all values. Maybe you can try 4 values out of this integer. Okay, so that reduces, of course, a lot of the state space. Also, you have what we call irrelevant variables within the model. So it's not in the incoming messages, but within the model. So maybe, for example, you have a counter in a loop. This is not really relevant to the overall state. Okay, you make a loop. At the end of the loop, the counter has a different value, but it doesn't really matter for the overall state. So these are all these things you can configure and say, okay, this is not relevant, and so on. Another thing is to limit the number of messages that could come in, because in theory, when you have message queues, you can add message queues in your queue forever, and it's a different state, but it's not really interesting. Okay, so you can limit the number of messages in the queues, and you can also say the messages inside the model have priority over the messages coming out. External from the model. And last, how do we end exploration? So the easy one is we don't have anything else to do, or we have already met the state, so we know we have already explored that state. We have reached the maximum number of messages. We detected a deadlock, execution error, you know, like a variable badly assigned, or improper value, or maybe outbound of an array or something like that. Or properties violated, of course. It's also something we are interested in. And in any case, a scenario will be generated to go back a path that will lead to one of these problems, and you can then analyze. So we tried it on we implemented that and tried it on a simple use case. So that's the demo example, the access control system. So it's a system where you you have a lock on a door and you slide your card, you have a PIN code and you're allowed to get in or not. So that's basically it. So the inputs are a card with a card ID and a PIN code with 3 or 4 digits. So it's quite simple, but actually if you combine all these parameters, for example, the card ID can be quite big. So if you want to try all the card IDs, which is not very interesting actually, you can create a huge amount of states, which are quite useless. But so we thought it was a good scenario because it's quite small, quite simple, but still has some problems in the sense it has enough complexity to do that. So that's what it looks like in SDL. You can see the channel going to the environment and the 2 messages coming in, and the 2 messages have the parameters described in the data types, and you configure, you limit the number of incoming messages and the values of the parameters. So you say, for example, here the card, you only have 4 different cards and only 3 messages of these 4 different cards. And also the keys you can type in is 0, 1, 2, 3. So it's only 4 values. You don't go up to 9. It doesn't bring any value to this. So we tried that, and since we already had an export to if, which is the format for the tool from the Verimag. I don't know if you're familiar with that, but the tool they've been doing modern checking for a very long time, and so it was a good reference value to see if the number of states explored was valid. So you can see it's similar. So it's not exactly the same, and that's mainly because if the format for Verimag is using what they call observers, and an observer is something you add to the state machine, and it actually creates state because it adds a new state machine as an observer to your model. So it creates actually more states. So you see it's quite similar. And the other one we tried, the symbolic tool from the CEA in Paris. And the number was only a few thousand, which is quite good. But as I said, if you increase the complexity of the model, it has some trouble for analysis. And also there are some concepts we have a very hard time to translate into their representation. Sorry. So as a conclusion, so as I said, the system has not been modified at all. It's the same model. The execution engine is the one you use to verify the model was correct. The results we have are comparable to other mature technologies. And the thing is, it's quite easy to take in hand because you stay within the same tool, okay? It's you don't have to go out to another tool and learn maybe how it works or how you configure it in the other language. So it looks very promising, and we have tried it on a toy model, and we are waiting to experiment it on a real model. Sorry. And I'm done. Okay.